Hi everyone! So today we are going to talk about the chemical reaction of coordination complex. So we have learned about the bonding theory of coordination compounds and complex. Now we move to the real business about the reactions of the coordination complex. Talking about their reactions, there are two major kinds of chemical reactions that we care about. And the first one is a redox reaction. And the second type of reaction is called substitution reaction. So now think for a second, what is the major difference between these two types of chemical reactions in terms of the change of their oxidation state, in terms of how the compound undergo the transformation? So now you think for yourself for 5 seconds. Okay, so the major difference between redox reaction and the substitution reaction comes in whether there is an electron transfer between species, between different reactants. For example, if you have a redox reaction, the oxidation number of the metal center will change, but for a substitution reaction, the oxidation number of this metal center will not be affected. So today our focus is to look at the substitution reaction, and specifically we want to look at one kind of reaction called ligand substitution reaction, or another name for this type of reaction is called ligand exchange reaction. So either way is the correct name for that, ligand exchange or substitution reaction. So what exactly is a ligand exchange or substitution reaction? I want to give you one example. So most of you have learned biochemistry, and you know that nowadays to kill cancer cells and cancer therapy is a very important thing. Many research centers and pharmaceutical companies actually are developing approaches to cure cancer cells. And one cancer therapy approach is actually to destroy the DNA of the tumor cells. And organometallic compounds or coordination complex are commonly used to do this job. But we know that we have healthy cells, we have the tumor cells in our body. How can we specifically target the DNA molecule of the tumor cell instead of hurting the healthy cell in our body? So one of the research I want to use as an example, you can actually read the original study in the paper I upload on iLearn. So there is a ruthenium complex. Okay, so we have the ruthenium metal center, and there are 3 ligands attached to this ruthenium metal center. The first one is a ring, okay, and the second ligand is ethylene diamine, which you have 2 nitrogen attached to this ruthenium metal center. We know this is a biodentate ligand. And the third ligand is we use the symbol X to represent the ligand. And examples of this ligand can be halides or something else. So depending on the chemical activity of the compound that we are looking for, we have the freedom to switch out these ligands. So why this actually is important to tune the chemical activity? We know that when we have this coordination compound in our body, and to activate the chemical reaction of biomolecules such as DNA, one very important step involved is hydrolysis. And what is hydrolysis? So by its name, we know water is involved for this process. And looking at water, we learned in the acid and base chemistry, water itself is actually a Lewis base, which has the lone pair, right? So when the water attacked to any of the ligand inside the molecule, there is a possibility the water can switch out this ligand. For example, the halide here, and attach to this metal center which is the Lewis acid. So that is the chemistry behind the hydrolysis process. In terms to understand the hydrolysis of this compound inside a biological system, it's very important to understand the switching between the water ligand or aqua ligand, as we name it in coordination chemistry, and this X, for example, halide ligand. So how does this switching job is going on and how does this occur? That's what we are going to study today. So in ligand exchange substitution, and this is one example that's shown here. Okay, so after we know ligand exchange matters so much, the real chemistry questions we are trying to answer involve two different aspects. The first one is thermodynamics. And the second aspect is kinetics. Okay, so we're going to see how these two aspects of this chemical reaction will make a difference in terms of the chemical reaction. Before that, let me show you one more experiment that we can actually do in the lab. So for example, in the lab, you have a beaker and you fill the beaker with some solution, and the solution is nickel coordinated to 6 water molecule. Okay, this transition metal complex carries 2+ positive charge, and this is what's inside the beaker. Okay, so now if I decide to inject ammonia or amine ligand into the solution, what do you think the chemical reaction is going to happen? So what is the phenomenon do you expect to observe after we add amine to this nickel solution? Okay, so if we run that reaction, what we can actually see is this nickel coordinated to water is green in color. But after we inject the ammonia into the solution, this compound will turn into a pale blue color. You can see a very distinctive color change after we add the reagent into the solution. So the chemical reaction we can write down actually involves the nickel coordinated to water. When we add ammonia, we are generating something new, which gives me the pale blue color. And in reality, the product we can get out of here is the nickel metal center now coordinates to this amine ligand. Okay, so all the water ligand, aqua ligand has been switched out by this amine ligand and form this complex, and the water has been switched out. To balance the equation, we need 6 amine and 6 water has been switched out. The color for the resulting solution is actually blue. Okay, so depending on the color change, we can already tell, okay, there must be a chemical reaction going on. Experimentally, you can use a UV vis to detect the exact absorbance of the final product after you put in amine ligands into the starting solution. But now let's try to discuss what is the chemistry behind this sample reaction. Okay, so the first piece of information I want to tell you is I can measure the equilibrium constant since this is an equilibrium reaction. The equilibrium constant or formation equilibrium constant for that is actually equals to 4 times 10 to the 8th power. Okay, look at the magnitude of this equilibrium constant. What do you think? Now, if we try to review what you learned about equilibrium in general chemistry, you can actually find out this is a huge number, which means the reaction favors to go to the product side. We are going to form the product thermodynamically in a very favorable way. So why is this chemical reaction will lead to the formation of a really stable compound compared to the starting one? And what is the rate of this chemical reaction and how does this chemical reaction happen. These are all the two major questions we are trying to answer in the rest of the lecture. Okay, so first of all, to give you a very straightforward visual idea how this is happening, so imagine this is our nickel coordinated to 6-water ligand, which is an octahedral shape for the compound and complex, okay, which is green in color. Now, for some reason, I try to put in the amine, the new ligand, okay, so how the ligand is going to interact with the compound, we don't know the process yet, but we know in the end, we are going to get a new compound where the nickel metal center is coordinated to 6 amine ligand, still an octahedral shape. Okay, so that's what we know. This is my starting material and this is my final material. How is this going to happen? So in reality, the substitution or ligand exchange process is happen by switching one ligand at a time. So to show you a model, so each time one of the water ligand or aqua ligand is switched out by one amine ligand, so which will give you a new molecule, and then we can switch out the second aqua ligand, the third, the fourth, the fifth, and the final one, which will give me the final coordination complex with 6 completely different ligands. So that's physically how this process generally is happening. Okay, now let's look at the thermodynamics of this process. So how to describe the thermodynamics of a process? We know that the K equilibrium constant is very large, so the equilibrium constant or formation constant can be a measure to determine the stability of the final product compared to the reactant. So that's the first consideration. And the second consideration, if you recall your general chemistry knowledge, every time we talk about thermodynamics, we need to talk about the change of free energy, right? How to calculate the free energy change? There are 2 major components, the enthalpy change and the entropy change, which give me the equation delta G equals to delta H minus T times delta S. And in chemistry or a lot of branches of chemistry, people usually will discuss for the delta G to be less than 0, which is a spontaneous chemical reaction, I want to know which component actually contributes to the spontaneity of the chemical reaction. Is it enthalpy or is it entropy? So if you have a really negative enthalpy, maybe the enthalpy is playing the dominant role in determining the thermodynamics and free energy of this reaction. But in some other cases, the delta S is actually pretty negative. The minus T delta S is pretty negative, which plays the dominant role for this chemical reaction. So that's why sometimes you can hear the terminology, is the entropy determine the reaction or is the entropy driven chemical reaction? This is where that comes from in terms of the consideration of thermodynamics. Okay, so now we know we have the nickel coordinated to aqua ligand, we have the nickel coordinated to amine ligand. What if I use a different ligand for the substitution job? What is going to happen? Okay, so let me tell you that if we use ethylene amine, which usually we use En to represent it, if we use ethylene amine to do this job compared to the amine, and we are going to get a different equilibrium constant. So do you think the equilibrium constant is going to be greater than 4 times 10 to the 8th, or is going to be smaller than this number? Okay, so actually the equilibrium constant is going to be approximately 2 times 10 to the 18th. Okay, so what do you find about these 2 equilibrium constants? When we use the ethylene amine as the ligand to switch out the aqua ligand compared to amine ligand, we are going to get a 10 order of difference in the equilibrium constant, which means this the resulting compound by using ethylene amine as an incoming ligand is so much more stable compared to the amine ligand attached nickel complex. Why that is the case? So that's my question. And the explanation underlying the dramatic difference or stability of the nickel ethylene diamine compound compared to the amine coordinated nickel compound, the difference is actually due to the ethylene diamine is a bidentate ligand and amine is a monodentate ligand. So this phenomenon is called chelate effect. You may heard about the chelate effect in analytical chemistry and biochemistry. So what is chelate effect? So to make it short, the chelate effects when you have a chelating ligand, will form more thermodynamically stable compounds. Okay, so that's the general phenomenon and the general reason behind the completely different equilibrium constant. So after this lecture, please go to iLearn. You can actually see the practice example and the practice questions. Please work that out to further understand the thermodynamics of the coordination compounds and their relationship in ligand exchange reaction. Okay, so now after we talk about the thermodynamics of the chemical reaction, we are moving to talk about the kinetics. So thermodynamics talks about the possibility of a chemical reaction, whether a reaction can occur or not. When we put the chemical reaction in reality, what we care more about is the kinetics. What is kinetics? Basically, is how fast the reaction can proceed. If the reaction can occur spontaneously, but it may take 1,000,000 years, who cares, right? So we want a chemical reaction to proceed at a reasonable rate that we can observe that can satisfy the needs of chemical production and some other applications. So in that sense, kinetics of a chemical reaction is super, super important. Okay, so now looking at the ligand exchange reaction, what's being involved in this chemical reaction or in this reactant we can analyze. We have the metal, we have the existing ligand, we have the incoming ligand. So which factor is going to determine or affect the kinetics of this kind of ligand exchange reaction? So that's my question. Now you can think for a few seconds and then come back to the video. So, okay, now we are going to talk about the factors affecting the equilibrium, the kinetics of the ligand exchange reaction. Okay, so before I tell you the conclusion and the results, please pause the video for a minute and go to the slides that on iLearn that I posted. Please go to slide 4 and read the table about all the rate constant for the ligand exchange reaction for different first row transition metal center, and then come back to tell me the conclusion. Okay, so now what have you observed in regard of the reaction rate constant of different first row transition metal complex in this ligand exchange reaction. So you may have noticed that depending on the metal species, you actually got completely different reaction rate constant, which means the ligand substitution reaction occur at a completely different rate for this different metal. Then it's very safe to make the hypothesis to say that the metal center plays an important role in determining the kinetics of this ligand exchange. But which aspect of the metal centers that are important for determining the kinetics of the chemical reaction? It's actually the electronic property of the metal center. What do I mean by electronic property? We can use the number of electrons in the d orbital to quantify the electronic property of the metal center. In other words, the number of electrons in the d orbital will play an important role to determine the kinetics of the ligand exchange or ligand substitution reaction. So I'm going to go ahead and introduce you a few observations that people summarize based on their empirical experimental data and the experience or rule of thumb people utilize a lot for determining the kinetics of the coordination complex. But before that, I want to introduce two new terminology to describe the kinetics. So normally when we say a chemical reaction, we usually say, oh, it's really fast, it's really slow. But in terms of describing the kinetics of a ligand exchange or substitution reaction, commonly people use the two words called labile and inert to describe the kinetics. Okay, so by just looking at the word, you can take a guess. Labile actually describe a really fast kinetic reaction, and then inert describe the really slow kinetics. But how fast a labile chemical reaction is. So usually when we consider a chemical reaction, when we put the reactant into the starting material, the moment we inject the new agent, we see the phenomenon of new compound formation, or the moment we inject the reactant, the reaction proceeds to its conclusion. We usually say this reaction is pretty labile, and contrary to that, it's an inert chemical reaction. Okay, so after we talk about the new terminology about labile and inert, now we're going to discuss which type of metal center are going to be labile and which type of metal center are going to be inert. Okay, so first of all, the fundamental rule determining the labile and inert property of the metal center goes back to the ligand field stabilization energy. Okay, so if you do not recall what is ligand field stabilization energy and how to calculate ligand field stabilization energy, you can go to previous lecture where we do a lot of discussion and practice on this aspect. So usually the more negative the ligand field stabilization energy, the more inert for this complex to undergo the ligand exchange reaction. Okay, so the more negative ligand field stabilization energy, the more inert of this reaction. This is the general rule of thumb. And to summarize a few common observations, we can say that if you have a metal and you have the 2+ and you have the 3+, And most of the time, the 3+ is more inert compared to the 2+ one. So the 3+ metal center is actually more inert compared to the 2+ one. That's the first rule. Okay, and the second rule is, so we have the first row of transition metal, the second row of transition metal, and the third row. Usually the first row of transition metal are called 3D metal, and the second and the third are called 4D and 5D transition metal. So the 4D and 5D are usually very inert. Why? Because these are really heavy transition metal centers, so they are more inert undergoing this ligand exchange reaction. So they are more inert compared to the 3D. Okay, then how about the 3D transition metal? Okay, so for the 3D transition metal, although they are lighter, but depending on the number of electrons in the 3D metal, the result can be different. So if you have D3, D8, and low spin D6, this type of electron configuration, they are usually inert compared to other type of D electron. Okay, so these are the 3 very common observation people find out about the kinetics of metal compounds in the ligand exchange reaction. So now we talk about the metal center. The first variable that we care about is the ligand going to make a difference. For example, if I have amine as the incoming ligand, or I have ethylene amine as an incoming ligand, how the ligand is going to change the kinetics of the ligand exchange reaction. So let's look at the effect of the ligand on this chemical reaction for together. Okay, so now you think for a few seconds to yourself. Okay, if you have the ligand incoming to switch out the old ligand, what's going on here? What is the chemistry and what is the major change for this compound? Let's look at the chemical reaction together. So we have this original coordination complex. Now I'm going to switch out one of the ligand one by one until I get a new complex where all the old ligands has been switched to the new one. Okay, so if we look at the model, you can actually find out when we try to replace the old ligand with a new one, the essential thing is to break a chemical bond and form a new chemical bond. That's the most important and fundamental aspect of this ligand change reaction. So in order to form a new chemical bond and break an old one, do you think it's an easy job? No, of course not. Then how is this process going to happen? So using the analogy of the SN1 and SN2 reaction in organic chemistry, we can actually find a very similar reaction mechanism in terms of the ligand exchange reaction. So let me draw you the reaction coordinate first of all. So if we look at the reaction coordinates of this ligand exchange reaction, there are actually 2 possibilities for the bond formation process. Okay, assume my compound is metal attached to a ligand X. And now I'm going to add a new ligand, which is Y. Let's see how the bond breaking and bond formation occur. Okay, so the horizontal axis is the reaction coordinate or reaction extent or extent of reaction. They are basically the same. Reaction extent. Okay, and on the y-axis is the free energy, which is G. In the first type of reaction mechanism for the ligand exchange reaction, we actually have the starting material, which is metal coordinated to X, and we add Y as the incoming ligand. And the reaction need to go through some intermediate states. Okay, so what is the species at the intermediate state? In the first type of reaction mechanism, people say that, okay, so we actually got the bond breaking between the metal and the original ligand, which is X. Okay, so these two are apart from each other, and then we add the Y ligand to this compound, and in the end I got the metal coordinated to the new ligand Y and leaving the original ligand X out. So that's the first type of reaction mechanism people observe and propose to describe this type of reaction. And this type of reaction mechanism is called dissociative. Reaction mechanism. If you try to still recall the substitution reaction in organic chemistry, you can actually find out the dissociation mechanism is very identical to SN1, right? How about the second type of reaction mechanism? If we look at the reactant, which is the metal coordinated to X, and we add the Y as the incoming ligand, okay, what's going on at the transition state? So at the transition state, what we found is actually the bond breaking and the bond formation kind of occur at the same time. So while X ligand is leaving the metal center from one side, the incoming ligand is attacking the metal center and try to coordinate to the metal center from the other side. And in the end, we are achieving the same product, the metal coordinated to the incoming ligand Y and leaving out the old ligand X. So you can see in terms of the reactant and the product, these two mechanisms are exactly the same. The only difference of these two reaction mechanisms comes in what is the intermediate state. So the second type of reaction mechanism is called associative reaction mechanism. So now you know dissociative is very identical to SN1. How about associative? Yes, it's very similar to SN2. Okay, so SN2, we know that the incoming ligand is attacking the metal center from a different side, and that might change the orientation of all the other ligands surrounding the metal center. And there is one joke that I can think of every time there's a strong wind. So in the wind, usually your umbrella is going to flip, like the orientation of the compounds in associative mechanism. And usually I would joke to my friends, so to test whether your umbrella is strong enough, you want to see whether your umbrella undergoes associative mechanism or SN2 chemical reaction route in the strong wind. Okay, so that's an extra topic here, but overall, in terms of the influence of the ligand in affecting the reaction of ligand exchange, we can see there are two quite different reaction mechanisms. One is called dissociative and one is called associative in terms of how the ligand comes and how the ligand go. Okay, so let me quickly draw what is the schematic of the ligand change in these two reaction mechanisms. Okay, let me using a different color. So in the dissociative reaction mechanism, assume you have a metal and it's originally attached to the X ligand, and all the rest of the ligand is actually ligand L. Let me call them ligand L. Okay, so suppose this is an octahedral shape. So this is my this is actually my coordination complex, then I'm going to switch out the X ligand. So what's happening is the X ligand is going to detach from the metal center, first of all, okay? And then after that, the incoming ligand, okay, which is Y, which is a Lewis base, right? So it got a lone pair, then can attack the metal center and coordinate to the metal center. The second step for this reaction can be shown. Okay, so once the X left the metal center, we have an empty spot. Let me use a different color so we can see where the ligand is coming. I'm using this orange color for all the ligands. Okay, so arrow ligand, arrow ligand, arrow ligand here, arrow ligand here. Now you see the spot where X is occupying now is empty, and it's perfect timing for the Y to attack the metal center and attach or coordinate to the metal center. And in the end, we are going to form the new complex where the metal center now attached to 6 ligand, and one of them is the Y ligand, which is the incoming new ligand, not the old one, the L. Okay, so this is how the reaction occur and proceed. Okay, in addition to dissociative reaction mechanism, let's see what happens in associative reaction mechanism. Let me use A to represent this type of chemical reaction. So in associative reaction mechanism, still I'm using green color to represent the metal center, and I have 6 ligands attached to that. One of the 6 ligand is the X ligand. Okay, so that's my X ligand, and the Y ligand is hanging around with the lone pair, try to coordinate to some empty orbitals in the metal center. Okay, and in this case, while when X tried to leave the metal center, and Y is trying to attack the metal center at the same time. Okay, so this happens at the same time. At a certain point, we can see that the metal kind of coordinate to the ligand. So the new ligand tried to coordinate to the metal center, while the old ligand X is moving away from the metal center. And in the end, what we get is still the same results. So the metal is coordinating to the incoming ligand Y, and the rest of the ligand keeps the same. Of course, in the second step, you can try to exchange the second arrow ligand until you switch out all the ligand to the new incoming ligand. But in one step, usually we switch one ligand at a time, and you can do this 6 times. What you need to pay attention to is, even we switch out all the ligands, so for every single step of switching out the ligand, the kinetics will be slightly different. It's not exactly the same reaction rate constant, they are actually different. So in terms of the influence of ligand, for the ligand exchange chemical reaction, there are 2 major reaction mechanisms, dissociative and associative. And here is the schematic of how this is happening. And so after this, please go check the practice problem which I posted on iLearn. the same place as this practice question, and you have more chances to work on the reaction mechanism on the ligand exchange chemical reaction. Okay, so now to briefly summarize what we have learned today. We talk about the bonding theory about coordination compounds. Now we try to learn more about the reactions of this coordination complex. There are two major types of reaction regarding the coordination compounds and the complex. The first one is redox reaction, where electron transfer can occur. And the second type is the ligand exchange reaction or ligand substitution reaction. We use the example of the nickel 2+ coordinated to aqua ligands, and we try to see how does the amine ligand switch out all the aqua ligands for this type of ligand exchange reaction. For this type of reaction, we usually need to understand them in two aspects. The first one is thermodynamics. When describe the thermodynamics of the chemical reaction, two parameters actually can be taken into consideration. The first is equilibrium constant or formation constant for this new compound. And the second component, you can calculate what is the Gibbs free energy change for the whole reaction. From there, you will get an idea how stable the new compound is and how spontaneous the reaction is about to happen. Okay, and we need to pay attention to that. The chelate effect, when we have chelating ligands, which is bidentate or multidentate, usually they are more thermodynamically stable compared to the monodentate. Using an analogy of a claw, try to secure one thing. If you have more points to anchor to the metal center, is actually more stable, which makes more sense. So you can check out the practice problem on iLearn to review this portion. Moving to the kinetics for the ligand exchange reaction, there are two components or two variables that will play an important role. The first one is the metal centers. Okay, to describe the kinetics of the ligand exchange reaction, first of all, the terminology we use is whether the reaction is labile or inert. Labile means fast and inert means slow, basically. Okay, and the criteria to look at is the ligand field stabilization energy of this metal center. Okay, so the more negative, the ligand field stabilization energy, the more inert. And there are 3 rules of thumb that you can memorize, which helps you to identify an inert and labile chemical reaction. So basically, the metal 3+ is more inert compared to the metal 2+, and one example would be iron 3+ and iron 2+. Okay, so if we have 4D and 5D transition metal centers, because they are heavy, usually they are more inert compared to their 3D counterparts. And for 3D transition metal centers, if the number of electrons in the d orbital is 3, 8, or if we have a low spin d6, and usually these type of compounds are more inert compared to others. Okay, in terms of ligands, how ligands are going to affect the reaction kinetics of the ligand exchange reaction, we need to first of all talk about the reaction mechanism. So very identical to SN1 and an SN2 reaction, we got dissociative and we got associative, in where the dissociative needs to cleave the metal and the old ligand bond before the new bond can be formed between the incoming ligand and the metal center. While for associative reaction mechanism, the breaking of the old bond and the formation of the new bond kind of occur simultaneously, and where you form the transition state where both ligands are present. And in the end, you are going to have the new compound where the incoming ligand switch out the old ligand. Okay, so to review these parts, please finish the practice question on iLearn I posted. And that concludes our story about the ligand exchange chemical reaction of coordination complex for today. If you have any questions, feel free to talk to me after class. Thank you.